Now we have to do STP. STP stands for Spanning Tree Protocol. Now, what is Spanning Tree Protocol? Spanning Tree Protocol is the protocol used by default on the switches that is enabled and is used to avoid loop formation. So first of all, it is used to avoid loops. This is the purpose of STP. This is default enabled on the switches. Now, how the loops are generated. First of all, to understand how the loops are avoided, you should know how loops can be generated. So for that, let's take an example. Let's say we have two switches. And they are connected together like this. Switch 1 and switch 2. Okay. Suppose a frame is received by the switch. Inside the frame, there is a source MAC address and destination MAC address. If the source MAC address is a broadcast MAC address, in that case, what the switch will do, the switch will receive the frame. It will see that the source MAC address is a broadcast MAC address. So it will not send the frame directly, it will send an ARP request in case it's unknown. But if it is particularly for broadcast MAC address is FFFF, then it will broadcast. So in two cases, either if the destination MAC is unknown or if the destination MAC is a broadcast MAC address. In that case, there are chances of loops. And if the switches that are connected together are connected via redundant link. In case of single link, it will not happen. Because in single link, switch will simply receive and forward to the switch on the same link, on the single link. But they are connected via multiple links. In that case, and the multiple links can be due to any reason. For redundancy, for failover purpose, we have connected the switches by redundant link. So if both the links are up at the same time and both the ports are receiving the frame and sending the frame, in that case, in case of broadcast, a loop will be generated. How? So if the frame is arriving here on this port, the frame has arrived here on this port of the switch. Suppose the frame is a broadcast frame, meaning that the MAC address in the source field, the source MAC address is a broadcast. Source MAC is FF, like this. This is the broadcast frame. In that case, what will happen? The switch will forward it out all other ports. Similarly, when the switch 2 will receive the frame, the one that it received from the upper port will be forwarded out on this port and this port. Similarly, the one received from the lower port will be forwarded to this port and this port. Okay. So this right here in between the switches, this is a loop. Yeah, because the frame will keep on revolving between the switches because of the redundant links. So this is how a loop is generated. So the formation of loop can be in case, first of all, if switches are connected via redundant links, more than one link. Second thing, if a broadcast frame is received, frame or frame with unknown destination MAC. So if the destination MAC is a broadcast or if the destination MAC is unknown, in that case, the switch will broadcast. So due to redundant links, loop will be generated. So in such a scenario, there are loop formations. This is destination. Okay, so this is how a loop is generated. So to avoid this type of situation, there is STP, spanning tree protocol, which runs by default on the switches. So what it do basically is it avoids formation of loop by blocking some ports. The unnecessary ports are blocked. So it uses some election processes to elect which will be the active port. So the active port only will come up and the other ports will go down. So at a time, only one link is active between the switches. Even if you connect the switches with 2, 3, 4, or 10 links, only one link will be up at a time and rest will be in the standby state. That is what STP do. So that no loops are avoided. So redundancy is there. If the active link goes down, one of the standby links will come up. So there is redundancy, but only one link is up at a time. So in this, in STP, there are some election processes involved that you have to know. First of all, how STP works. First thing is a root bridge is elected. A root bridge is elected. Here in STP, the term for switch is used as bridge. Actually, the technology came when there were bridges used. So nowadays we don't use bridges. Now we have switches in place of bridges, but the term remains the same because it was the earlier technology. So root bridge is elected. So one of the switch becomes the root bridge in a redundant topology. Then root ports are elected. Some ports are elected as root ports. We will see which ports become the root ports. Then the designated ports are elected. Some ports are elected as designated ports. And rest all the ports that are left after the root port and designated port election are blocked. This is how STP works. For electing all these root bridge, root ports, designated ports, and block ports, there are some election processes involved. So the election process is the next that we have to see. Okay, so the path cost is elected and the path cost depends on the bandwidth. If the bandwidth is, let's say, Ethernet, if the port is the Ethernet port, then the path cost will be 100. So higher the bandwidth, lower is the cost. Fast Ethernet ports have the bandwidth 90. Gigabit Ethernet ports have the cost 4. 10 gigabit Ethernet ports have cost 2. This is the table of the path cost. These are the fixed path costs for different bandwidths. So using this path cost, the election of the lowest path cost is done. So the port with the lowest path cost becomes the root port. If, let's say, the path cost is the same, in that case, we look for the lowest bridge ID. Now, bridge ID is what? Bridge ID is the combination of priority and MAC address again. It looks for the lowest priority. If priority is same, then lowest MAC. If, let's say, bridge ID is also the same in this case, then the election process is done on the basis of lowest port ID. That is the tiebreaker. This is how root port election is done. After the root bridge election and root port election, root bridge election is done on the basis of lowest priority, lowest MAC address. This combination of priority and MAC address is called bridge ID. Bridge ID, the combination of priority and MAC address. Okay. After root bridge election, root port election is done on the basis of lowest path cost. Path cost is on the basis of the bandwidth. Higher the bandwidth, lower is the path cost. If path cost is the same, then the root port election is done on the basis of lowest bridge ID. If bridge ID is the same again, then lowest port ID is the typewriter. Next is the designated port election. Now, designated port election is done on the basis of the same way like the root port election. So we can just write it as same as root port election. That's it. For block ports, that is the last election. Block ports doesn't have any election process. Whatever is left after the root port and designated port election are all blocked. So let's see with an example now. We have two switches connected together via redundant links, switch 1 and switch 2. So the redundant links are 2. The ports are fast Ethernet 0 by 1, fast Ethernet 0 by 2, fast Ethernet 0 by 1, and fast Ethernet 0 by 2. These are the ports. Now, in this case, how the loops will be avoided, we'll see. So here, let's say the priority of switch 1 is 32768 and MAC address is 111. I'm just taking any number. And here priority is 32768, MAC address 222. Okay, and both are fast Ethernet links in between the switches. So in this case, what will happen? So first thing is the root bridge election. Root bridge is a switch in that network. So in this network, one switch will become a root bridge. Which switch will become the root bridge? That depends on the election process. The election process says the lowest priority and lowest MAC address. So first is lowest priority. First thing it will look for is the lowest priority. Between switch 1 and switch 2, the priority are 32768, which is the default priority, and switch 2 also have the priority 32768. The default priority is set, which is the same for both. So in that case, it will look for the lowest MAC address. MAC address of switch 1 is 1111 and switch 2 is 2222. It's just simply the hexadecimal digits. It looks for the lowest one. So switch 1 in this case will become root bridge. Yeah. So this will become root bridge. Now, one thing is to be noted that once a root bridge is elected, all the ports of a root bridge are designated ports. So these two ports, both will be designated ports. TP is the short for designated port. So both will be designated port because designated ports are in forwarding state. They are always sending. So they are in forwarding state. So root bridge is elected. All the ports of the root bridge are always designated ports. Now the second step is root port election. Root port election is based on the lowest path cost. Root ports are always on the non-root bridge only, not on the root bridge. On the other switches, there are root ports and only one root port is there on one switch. So on switch 2, there are 2 ports. Out of these 2, one will be root port, one will be block port, because one has to block to become backup. Fine. So first the root port election will be done. Root port election is based on the lowest path cost. If you see the path cost, both the links gives you the same path cost because both are fast Ethernet links. So the path cost is 19, same. 19 for this link, 19 for this link. So path cost is the same. So the election process goes on the next step, lowest bridge ID. Bridge ID is lowest priority and MAC address. Both the ports are on the same switch. So the priority and MAC address is the same. So the tiebreaker will be the lowest port ID. So the port ID lowest is fast Ethernet 0 by 1. So this will become root port. And the last one, this will be blocked. So by this, only the upper link, this link, the first link that is up, and the lower link is down, that is in the standby state. So this is how the STP works. So it only allows one link to be active at a time and rest all are in standby state. Okay, so these election processes, you have to remember that how STP works, what are the election processes. Actually, we do not have to do it. We do not configure STP. STP is default enabled. But you should know how it works. You should know what are the election processes. But this works automatically. On the switches, this is done automatically. In case of redundant links, STP starts working itself to the election processes and automatically it only allows one link and rest are sent into standby state. So let's take another example for the same. Okay, now other example is this. 3 switches connected like this. Switch 1, switch 2, and switch 3. Fast Ethernet 0 by 1, fast Ethernet 0 by 2, fast Ethernet 0 by 1, fast Ethernet 0 by 2, fast Ethernet 0 by 1, and fast Ethernet 0 by 2. Okay. Now, let's say the priority of this switch is 100, MAC address is 111. Priority of this switch is 200, MAC address 352. Priority of this switch is 10, MAC address 3333. Okay. Root path costs are the same on every link, 19, 19, 19, because all are fast. Fine. Now let's start with the election processes. The first thing is root bridge election. Now, can you tell me which switch will become the root bridge and why? Which 1, 2, or 3? Which switch will become root bridge?
3.
Yeah. Why? Can you tell me why switch 3 is the root bridge? It's the correct answer, yeah. Okay, so switch 3 is the root bridge because of the lowest priority. Yeah. So switch 3 becomes root bridge. Now, as I said that once root bridge is selected, we know that all the ports of a root bridge are designated ports. So both the ports here designated ports. Designated port. Yeah. Now there will be root port election. Root port election is done on non-root switches. So both the non-root switch 1 and switch 2 will have a root port, and root port is only one. And root port is basically the one that gives you the best direction towards the root bridge. So if we start with switch 1, switch 1 has 2 ports, faster than 0 by 1 and faster than 0 by 2. So which one will become the root port? That is on the basis of the election process for root port. That is the lowest path cost first. The lowest path cost is, if you see from fast Ethernet 0 by 2, the path cost is 19 towards root bridge. And from the other fast Ethernet 0 by 1, the path cost is 19 plus 19. That is higher. So lower is 19, fast Ethernet 0 by 2. So this port will become the root port. Similarly, in case of switch 2 also, fast Ethernet 0 by 2 gives you the path cost 19 towards root bridge, whereas from the other link, 19 plus 19, that is higher. So this will become root port. Now root ports are elected between both the switches. Two ports are left now, one on switch 1, other on switch 2. So the next election process is designated port election. Now one of the port will become designated port and the other will be blocked. So the designated port election now is based on the same way like root port. Switch 2, one port is left. Switch 1, one port is left. Only one will be block port and other will be designated port, because root port election is already done and on any switch there cannot be more than one root port. So one will be definitely designated port. Now designated port election is based on lowest path cost, same as root port. So lowest path cost is, if you see from switch 1 port, it gives you the path cost 19. From switch 2, 19, same. So path cost is the same. Then the election will be done on the basis of lowest bridge ID, lowest center bridge ID. Switch 1's bridge ID is the priority and MAC address and priority and MAC address. That is the bridge ID. So the priority of switch 1 is 100 and priority of switch 2 is 200. So switch 1 has the lowest priority. So straight away, fast Ethernet 0 by 1 of switch 1 will become the designated port, and the last one that is left will be blocked. Yeah. So by this you can see for switch 1 and switch 2, one link is up only. Towards switch 3, one link is up, and the third, that is the redundant link, that is in standby state. If any of the active link goes down, then the third link will come up automatically. So this is how STP works. To see it, we do not have any lab to do in this STP because STP works by default. So you can just go and check by connecting switches with via redundant link and then see how STP converges and what are the elections done, which switch became the root bridge, what are the designated ports, root ports, by the command show spanning tree. I will show you. Okay. Root bridge, root ports, designated ports, everything. Priorities, MAC address, everything. So this is how spanning tree works. Okay, then there are a few things that you have to know, like in STP port types. We already discussed the port types are designated ports, root ports, and block ports. So these are the different port types in STP. Then there are STP port states. When STP converges, it goes through a few states. The first is the blocking state. Blocking is the first default state. When you connect switches with any device, you see the ports of the switch are first red, then they become amber and then green. So it takes some time. That is the STP convergence time actually, which STP takes to, and the switches port take to come up. That is the STP time. So blocking, from blocking it goes into the listening state. From listening it goes to learning state. From learning it goes to the forwarding state. So these are the port states of STP: blocking, listening, learning, forwarding. Then there are STP timers. What are these timers that it takes? So first is the hello time. hello time in STP is 2 seconds. Then is the forward delay time. Forward delay time is actually a 2 times cycle, which is 15 seconds. So it becomes 30. Then there is a max age time, which is 20 seconds. So these are the timers: hello time, forward delay time, and max age time. So basically what happens after blocking state, it goes into the listening state. In that it sends hellos. And in the hellos, it sends the bridge ID, which are called BPDUs. When these switches are connected, how the election process is done, whole election process is done with the help of the BPDUs. For example, when the switches are connected, they send hello packets. Hello packets is just to maintain the keep alive. Similarly, in the case of routing as well, the routers exchange hello packets to maintain the keep alive. Similarly, in switches, when switches are connected, BPDUs are exchanged, but BPDUs are not periodic. They are sent for the first time for election process. So BPDU is Bridge Protocol Data Unit. Bridge Protocol Data Unit is BPDU, which is exchanged between the switches, which contains bridge ID. It contains the bridge ID. So using this information from the bridge ID, the switches do the election processes. Bridge ID is the priority and MAC address. So using the information, the bridge ID is exchanged and the bridge router, the root bridge, is elected. Yeah. So after the bridge ID is exchanged, the BPDUs are exchanged, then the hellos are sent just to maintain the keep alive. So hellos are exchanged every 2 seconds. Then is the forward delay time. Forward delay time is the time that it takes to go from the listening to the learning state and then from learning to the forwarding state. So listening to learning, it takes 15 seconds, and then from learning to forwarding, it takes 15 seconds. So 15, 15, and 2 seconds hello time. That becomes 32. And there is max age time, which is 20 seconds, which in total becomes 52. So that is the total STP convergence time. The total STP convergence time is 52 seconds. So that is how STP works. It takes some time to converge. First of all, in which it do the STP elections. So the port states are blocking, listening, learning, and forwarding. The timers are hello time, forward delay time, max age time. That becomes the total STP convergence time, 52 seconds. So every port of a switch exact takes 52 seconds to come up. In the software, it do not take the exact 52, but in the real devices, it does. There is another enhancement feature by which you can avoid the STP to converge like this if on any port you do not want STP to take 52 seconds. For example, access ports. On access ports, because switch is connected to the PC, it's not another switch, so you do not have to do the election process between the PC and the switch. So on the access port, you can avoid taking 52 seconds to make it faster by configuring port fast. This is an enhancement feature called port fast. So port fast is enabled on the access ports to make the ports come up immediately without taking the convergence time, the 52 seconds, the port can automatically come up immediately with port fast. To do that, you have to go to the interface and enable port fast. So the command is spanning tree port fast enable. But we do not have to do the labs for it. In spanning tree, what you have to focus is the election processes. So you should know how STP works, what are the election processes. So first, in step by step, it's due. First thing is the root bridge election, then root ports election, designated port election, and the block port election. For these elections, what are the election processes? Root bridge election, root port, designated port, how they are elected, that you should know. Then timers, the port state, port types,